Hey guys, here's a quick video to introduce the next topic in rotation. If you remember, we talked about how everything that we did linearly is now going to be done rotationally. And after kinematics, we did forces when we were talking in a straight line. Well, now we're going to deal with forces that cause a change in rotation. So these aren't forces that are going to cause us to speed up or slow down like they did back in the first semester. These are going to be forces that are going to cause us to change our omega, right? They're going to cause an alpha. We call these forces torques. We give torque the Greek symbol tau. Again, torque is any force that causes a change in rotation. There are three things that are going to determine how much torque a force has. That is not what I was looking for. Oh, this is killing me. There we go. Let's say we've got this beam that we want to exert a force on that's going to cause it to rotate. For this purpose, let's put our pivot point or the point that it's going to rotate around at the end here. Almost think of this as like a door, right? A door is going to have the hinges. That's where the door rotates about. There are three things that are going to determine how much this object rotates based on the force. The first one is the size of the force. Right, the harder we push on a door, the more it's going to change its rotation. It'll start to spin faster, right? So the size of the force. The second is our distance from the pivot point. Right, I think at some point in our lives we've all tried to walk out the door of a store and accidentally pushed where the hinges were, realizing how hard it is to try to open the door from that point. Right, so three things: the size of the force, the distance from the pivot point, right? I'm going to get more rotation pushing here and less rotation pushing here. The last thing is going to be the angle of the force. And we're going to talk about it in terms of its relation to the radius of curvature. Right, the angle to the radius. For example, if I were to draw just a straight line going right through the center of this, that would be considered my radius. I'm going to get more torque pushing in a straight or pushing perpendicularly than I would if I was to, let's go a different color here, sorry, if I were to try to say push at an angle. Right? I'm not going to get as much torque out of this. These three things get us to our equation for torque. Our equation for torque is force perpendicular times r, or the distance. So if I can get back my my beam here, let's see if I can do this right the first time. There we go. Right, and if I wanted to calculate the amount of torque a given force would give, if this is my pivot point here, I'm going to exert my force here. This would be my force measured in newtons. And my distance from how far I am from the axis of rotation, this is my R measured in meters. So if I want to calculate my torque, it's going to be the amount of force perpendicular times R. Because force is measured in newtons and my radius is measured in meters, my units for torque is Newton meters. Now, our force, or excuse me, my pivot point does not always have to be at the end, right? I can change this around, right? We can determine, or a lot of times it'll just be given to us in the problem, where that pivot point, come on with this. And alive. Right, we could also have our pivot point here in the middle, in which case we would rotate around this way, depending on which way it was being pushed. Keeping in mind, counterclockwise is always going to be positive, clockwise is always going to be negative. Just like we had when it comes to our forces, we can have a total torque or a net torque. My net torque is really just all of my torques added together. However many I might have. And just like before, the torques in opposite directions are going to cancel each other out. Torques in the same direction are going to add together, except now instead of dealing with left, right, or up, down, east, west, it's all going to be about clockwise, counterclockwise. So, for example, let me go ahead and erase some of these on here. If I wanted to know my net torque, if I had, say, a force here and a force here, we'll call these force 1 and force 2. R2, R1, my total torque would just be T1 plus, tau 1 plus tau 2, which is really just F perpendicular for each one. These are going to get added together because both of these forces would cause a counterclockwise rotation. If, for example, I had a torque on this side, F3, well, that would now be a a clockwise torque. That would actually be subtracted. That would cancel out from it, just like if we had two forces going to the right and one force going to the left. Right, that one would be in the opposite direction. That's going to cause a different spin. That is going to cause a cancellation of torques, right? The last thing that I want to talk about with you guys when it comes to torque is the idea of the angle, right? The perpendicular portion of the angle. Now, what you need to remember, if I have a beam, right, and let's say here's our pivot point, and I have my force coming in at an angle here. We'll call this F. My distance, or my radius, we'll put this in a different color, would be there. We'll call that R. And you got to remember, the force is where the force is actually happening, not where it originates from. So we want to make sure we're dealing with the entire R here, because this is the point we're looking for. It is only the perpendicular component to the radius that actually does or creates any torque. So I'm going to need to break my force down into its components in order to figure out what that perpendicular component is. We're just going to call that F perpendicular. Depending on the angle that we are given, that's going to determine whether we're going to use sine or cosine. So I don't really like to get in the habit of saying, oh, it's always, FR times the sine of theta or FR times the cosine of theta, because it's all based on the angle that we're given, right? If that by chance happens to be my angle, in this case, my torque would be equal to F perpendicular times R. And I suppose I should. I'm sorry, this makes it look like that's my F. So when I go to calculate this, in this situation, F perpendicular in this case would be F times the cosine of theta times R, right, for this one. But that's not an always statement. It's going to be based on which angle we're given. Now, there's another way to go about this too, because it doesn't have to be, and you'll find that it works out to be the same, but it doesn't have to be the parallel component of the force. It could also be the parallel component of the radius. Let's say, for example, I've got a beam. Oh, this is not. That looks kind of like this, right? Here is my pivot point, and I'm going to deal with its own mass. We'll get to this later, but its own mass being the force that's acting on it, right? Now, what I can do in this situation, if up on the top, I use the entire radius and the perpendicular component of the force. In this case, what I can do, I can use the entire force, and instead of this being, if we were to, right, this is my R, but what I can do is I can extend my force down. Let's make this a different color. I can extend my force down, right? I'm not changing the amount of the force. I'm just creating my triangle here. And I can create my triangle, and I can use the perpendicular portion of my radius, right? If the red line represents the R, this would still be the same thing. It's going to work the same way. In this case, I'm going to use the entire force with the perpendicular of the radius. Up here, I'm using the entire radius with the perpendicular component of the force. We're going to practice these as we move forward with this. It still turns out to be the same, whether I use the perpendicular of the radius or the perpendicular of the force. The math is going to work out for us. Okay. For this, we're going to do some practice on this. Part of your assignment today is going to be to practice just calculating some torques, how much torque you get from different angles, things like that. We will meet tomorrow and we'll do a lab to kind of explore some of this stuff. If you've got any questions, feel free to send an email to either myself or Mrs. Fine Ice. Otherwise, enjoy your snow day.